All right, so here is our practice problem. I'm going to transition to the notepad in a moment to work this out, but as always, the actual examples work and the final solution are also included here in the slides. Okay, so we need to find the three cube roots for the complex number z equals -2 plus 2i. So let's go ahead and pull ourselves to the notepad. Let's talk about what we need to know. In order to make this work, I need to go ahead and have something to actually work with. One of the big things that I'm going to need is I'm going to need the magnitude for this specific, I keep saying magnitude. I need the modulus for this complex number in trigonometric form. I'm also going to just need this number in trigonometric form because we need an angle theta for us to do our work. So let's go ahead and transition that over. We've done this before. We're going to find r by taking the sum of the squares of the coefficients. So -2 squared plus 2 squared. So this will give us 8, or 2 square root of 2 for our modulus. For our angle theta, you've seen this before. We're going to say tangent of theta is equal to b over a, which in our case is 2 over -2 or -1. So when is theta equal to -1? Excuse me, when is tangent of theta equal to -1? Well, there are two places. This is either going to be in quadrant 2 or quadrant 4, since it's tangent being negative. And this is going to have a ratio of 1 between sine and cosine when we're at some pi over 4. So this is either 3 pi over 4. I'm going to clean that up a little bit. Either 3 pi over 4 or potentially 7 pi over 4. Which one do we want? Well, let's go ahead and revisit. We have a negative real and a positive imaginary. So negative real, positive imaginary, we're up in Q2. So in this case, the actual value for theta is going to be 3 pi over 4. Now keep in mind, if you're doing something like this with a calculator, you're going to get, in this case, a negative value. And it's going to be because the output for our inverse trigonometric functions, like arctangent or inverse tangent if you prefer, are going to output on that range, remember, from -pi/2 to +pi/2. So we had to do the extra interpretation step of saying, okay, what angle is that really? And also, which quadrant am I actually in? Okay, now we have a lot of the pieces. We're going to rewrite z. So this is 2 times the square root of 2. And that's going to be times cosine of 3 pi over 4 plus I sine 3 pi over 4. Now this is kind of an intermediate step for us here. We're just basically taking this and going one piece at a time as we go through. The one thing I want to talk about now is we're actually going to find those cube roots. So we actually want to go ahead and find the cube roots for all of these. For, excuse me, for not all of these, for z. The formula is going to be z sub k equals, this is something that you'll notice that they do a little bit differently in the slides. We're taking the cube root of 2 times the square root of 2. This by itself is pretty messy, so this is why in the text they do this instead. They leave this as the square root of 8, and then use the properties of exponents, since those apply to roots, to rewrite this as the 6th root of 8. I don't really like that they just jump straight to this, so I wanted to kind of explain where it's coming from. The cube root of a square root is the same as taking the 6th root. Okay, that gives us the first part. Now we need to go ahead and fill in the rest. So this is times cosine of, up top, this will be 3 pi, plus 2 pi k all over 4. And we'll have the exact same thing except for I sine. This will be I sine of 3 pi plus 2 pi k all over 4. Then from here, we're going to take our k and exchange it for 3 values. We're looking for the cube root, so k is going to be 0 1, and 2. So basically, I'm going to take this formula and replace these two k's with this value, and this value. That'll give me my 3 roots. So in other words, the first of our cube roots is going to be the 6th root of 8 times cosine of just, in this case, 3 pi over 4. Since taking k to be 0 just ignores this piece, plus I sine of 3 pi over 4. This isn't actually too bad to evaluate. We could go ahead and actually find these values. We know that cosine at this is going to be negative square root of 2 over 2. We know that sine at this position is going to be positive square root of 2 over 2. That is an option. But the thing is because we're already dealing with a cube root of a square root out front, we also kind of need to talk about that a little bit. In this case, let's go ahead and see what happens. We have the 6th root of 8, which is just going to hang out. We're going to go ahead and call these square root of 2 over 2, negative in the case of cosine, plus positive square root of 2 over 2i. If I want to combine these, I need them to be essentially the same thing. I need them to be able to talk to one another. And as it is right now, they're not really in that position. So, and this is the part that, again, is a little bit tricky. You can kind of see for yourself what they do on the slides, where they just go ahead and skip straight to the end and say, oh, hey, this means that it's the square root of 2 times cosine of 45 degrees plus I sine of 45 degrees. There's a lot more going on than just that. For me, this is where I would ask you to stop. So with what you saw in the actual work on the slides, just kind of ignore where they're going with it. It makes a little bit more sense when we find the remaining 2 roots to just go ahead and approximate. But with the work that they're doing here, again, it's just a little bit overkill. So here's what our remaining roots are going to look like. Z sub 1 is going to be equal to the 6th root of 8 again, out front. Inside with our 2 arguments, since k is now increased to 1, we're going to have 2 pi plus 3 pi in each case. So this will end up being 5 pi over 4. So cosine of 5 pi over 4 plus I times sine of 5 pi over 4. And then replace those with their values. At 5 pi over 4, cosine is still negative, but now sine is negative as well. So this is the 6th root of 8 times negative square root of 2 over 2 minus square root of 2 over 2i. And again, I would ask that you leave it here. If you're doing this for WebAssign, this is what I would then take and put into a calculator. I would do the 6th root of 8 times this negative square root of 2 over 2 and get my approximation. That leaves us one last root to get. If we replace k with 2, we're now going to be adding 4 pi to 3 pi up top. So this will be 7 pi over 4 for each of them. So this will be the 6th root of 8 times, we know what the cosine of 7 pi over 4 and sine of 7 pi over 4 are. In cosine's case, we're back to positive, so this will be positive square root of 2 over 2. But sine is still negative, so this will be negative square root of 2 over 2i. And this gives us our 3 roots here. So the cube root of, again, remember at the very start, the cube root of negative 2 plus 2i, we have all 3 of them shown here. It's a little bit more difficult to discuss what it means to be the principal root in the case of complex numbers, but that's also not something we're really focused on here. The idea is, can we perform this using this formula?